Yeah, welcome. I am Amos Alalika Kemi. I'll be presenting on types of isomer in coordination compounds. Today, which is 9th of July, I'm speaking from San Carlos, Brazil, Oscar. And thanks to Professor Dr. Jan Mazel Halgalo for this wonderful opportunity to explore the QUI 701, the Advancing Organic Courses. My first slide will be talking about definition of isomers. And what do I mean by isomers? So whenever two or different compounds having the same the same formula, they are known as isomer. What I mean is that whenever two compounds or different compounds, they have the same molecular formula but different properties, that's when we term it isomer. And also we are having various type of isomer, but we have two principal types of isomers among coordination compounds, each of which is now further divided, which is what I now use a table, a pictorial illustration to explain. We have the isomer. These are the two principal types. We have the structural, we have the stereoisomerism. And talking about the structural, you have the ionization isomer, which is we have the hydrate isomer, we have the linkage isomer, coordination isomer, and coordination position isomer. So this is the subdivision of structural isomer. While the stereoisomer, we have the geometrical isomer and optical isomer. So now I'm starting with structural isomer. Talking about the structural isomer, we have the ionization isomer. I picked the first one, structural ionization isomer. From the name, it occurs when a ligand that is bound to the central metal exchange place with an anion or neutral molecule that was originally outside the coordination complex. It looks abstract. Let's go to my second slide. So this is what I'm trying to explain. We will notice that this is central metal ions. So we have in NH3, the ammonia, 5 ammonia, and Cl, chlorine. We notice what happened here. The Cl is outside, the Br is inside, the bromine. So what I'm not trying to say, the complex compound are having the same formula but different ions in the solution. You see now, this is the same formula, the pentamine chlorocobalt 2 bromide, pentamine bromocobalt 2 chloride. You can see they are having the same, but when they enter the solution, they are different. So dissolved in water, for example, you notice this is bromine ion is generated, here chlorine ion is generated, and when it's dissolved in water as well. So now talking about coordination isomer, this one is quite different from this, in that the coordination isomer occurs when there is an interchange of ligand between the metals in the cation and metals in the anion. Please take note of that. Metals in the cations and metals in the anion. So the total ratio of ligands in the metal remains the same, but the ligand attached to the specific ion changes. You know, I explained in my earlier slide, these are the ligands. This is a central metal ions. Look at what happened. For example, I just illustrated a single example. CONH36, CrCN6, CrNH36, CONH6. We will notice that here we are having CO. It changes. Cr. So NH3. So CO is now having CN6 over here, while Cr is now having NH3. So which is what I illustrated pictorially below. We can see cobalt in the middle, Cr here. So they change places. That is, the metals in the cation, the ligands, that is, there is an interchange of ligands. So the ligands is being changed from one metal to another. So that's just the simplified version of coordination isomers. So going to slide 3 now, we have the hydrate isomer, which is also, we also call it solvate isomer. So these are the type of isomer which have the same composition but they differ with reference to the number of solvent ligand molecule as well as the counter ions in the crystal lattice. So for example, you can see this, and note before showing the example, it's a special kind of ionization isomer where a water molecule is one of the molecule that exchange places. You can see now, this is a violet color, blue-green color, dark green color. You can see Cr, H2O6, Cl3. There's an exchange of water. So the example above, they tend to differ. They have different chemical properties upon reaction with what? AgNO3 to test Cl- ion. So we have 3, 2, 1 Cl minus ions in the solution respectively. What I'm trying to say is that whenever this example they are dissolving AgNO3, the chlorine ion that's been exhibited is different in that, talking about this, we have 3 chlorine, here we have 2 chlorine, here we have a single chlorine. So that's just a brief explanation on hydrate isomer. And talking about linkage isomer, it occurs in the case of ambidentate ligands, and I explained ambidentate ligands. Okay, I will explain ambidentate ligands again. So these are the ligands that have 2 different donor atoms in which the ligands can attach to the metal by any of them. So look at this, an ambidentate ligand, this an ambidentate ligand. So it can attach with the oxygen or attach with the nitrogen. So I made example here, SCN minus, NCS minus, SCN or NCN minus, NO2 or ONO minus. So that's the meaning of ambidentate ligands. They have 2 sides of attaching. So look at this now. This ambidentate ligands, they tend to attach to the central metal ions. They tend to attach to it. So we are having nitro isomer, CONO2, and here we are having COONO. So this is the nitrito. We call it nitrito isomers. So now progressing to my 4th slide, the coordination position isomer. The coordination position isomer, which is the last example for the 2 principal isomer that I mentioned, the first one. So this type of isomer is found in polynuclear complexes, that is presence of more than 1 metals. So we can see due to the exchange of ligands between the metals, we can see this now. So it's found in polynuclear complexes. So here we will notice that we will be having more than 1 central metal ions. So look at now this CO. So NH3 2Cl2, here we are having NH3Cl minus. You know the sphere I was talking about, this sphere. So and NH3 4CO, and here we are having NH3CO. So there is an exchange of ligands between these metal atoms, which is what I illustrated pictorially. Now going to the second type of isomerism, which is stereoisomerism. We are having geometrical isomers. So, and I thought we were having geometrical isomer and the optical isomer. So now this geometrical isomer is now of various types in which we must understand stepwisely. So this type of isomer shows the square planar and the octahedral complexes. It does not show the tetrahedral complexes. It shows the square planar and the octahedral complexes. Please follow what I'm saying. Square planar and the octahedral. So taking the first one, which is the square planar, I represent it with Ma4. So look at the Ma4. This. It's not showing any differences. So there's no isomers for this. And talking about Ma3b, I use M as a central metal atom, and I change the ligands A3A and AB. So we will notice that this is not an isomer for this. This is not an isomer for this. And if we take Ma4, even if no matter the way we write the A, it is not an isomer. And talking about Ma2b, Ma2B2, we have 2 isomers. We have the cisplatin. And talking about this cisplatin, is an anti-cancer agent, which is used as an anti-cancer, while this is detrimental to the body. So we will notice that this cisplatin is an isomer for this. We have 2 isomers. This is it. Cl is here, Cl is here, which is the cis. That's what we call the cis. That's where the cis generates from. Why Cl is here, Cl is here. This is the trans. So this is the NH3. So I am still under square planar isomerism. Talking about the other one, we're having MABCD. We have the C. MABCD. So we have 3 isomers for this. So we have the PT. Okay, I stated an example, platinum, which is the central metal ion, platinum, central metal ion, platinum, central metal ion. We will notice the changes in the three. Here we have NC5H5. Over here we will notice that the NC5H5 migrated here. We will notice another differences again. NH2OH is here, NH2OH is here, NH2OH is here. We will notice NO2. So there is the changes in the position of the ligands, which now give rise to 3 isomers. But the other ones I explained are which this is not having any isomers. These 2 isomers, and the C is having 3 isomers. So now progressing to octahedral, I just explained the square planar. So you can see it's in a square form. So I'm still on that geometrical isomers, but I will be explaining octahedral complexes, which is the second one. Look at the octahedral. This is the octahedral complexes. No isomer is formed here. When I represent my central atom as M, my A as 5, and my B as 1, I notice there is no isomer. And MA4B2, I notice 2 isomer. This is my B. I form 4 A's. So this is my A, and A, 3A and the last A, and this is my B, and this is my B. I notice formation of isomer, 2 isomer, BB, so which is the cis isomer, and this is the trans isomer. I notice BBB, and here I have BB and B. This is a trans isomer that was formed. I progress again by representing my central atom with MA, M, and my ligands as A3 and B3. So when I did that, I noticed 2 isomer. So the 2 isomer I was able to get is what I now represented as this, which is known as the facial isomer or meridional isomer. We call it FAC and we call it MA. So which is what I was able to denote from my Ma3 B3 isomer. So progressing to my last slide, which is known as the optical isomer. So this type of optical isomer, this is a type of isomer that is shown by tetrahedral and octahedral complexes. Let me take 2 steps back. Here it is shown by what? Square planar and octahedral, which I prove. This is square planar, and my octahedral, I proved it here. And here we notice that it does not show what? Tetrahedral complex. Look at what happened here. Inverse is the case. This type of isomer is shown by what? Tetrahedral and what? Octahedral. Why? This, it doesn't show what? Square planar. So these isomers are referred to as what? Enantiomers or enantiomorphs, each of each other. So it's known as the enantiomer or enantiomers of each other, and there is what? Non-superimposable structure are described as being asymmetry. I will explain that now. I will start from tetrahedral. This is tetrahedral. If we observe this, I represented by M, metal central ion as M, and I use A into 4 places. So I was able to notice that there is no isomerism. Why? Because it still remains the same. It still remains the same. So, but when I use M, A, B, C, D, I observe what? An isomer. Sorry for that. I observe an isomer because both are non-superimposable, like what I said here. So this isomer refers to an enantiomer or what? Enantiomorphs of each other, and there is non-superimposable structure. So which is what? Both are non-superimposable. That is, they are not the same. They are not the same. We will notice it's just like in form of a mirror image. This tetrahedral, a mirror image. They are not the same. So which is it's optically active. We have the levo rotatory and what? Destro rotatory, which is what happened here, and destro rotatory. But here, no matter the way I arrange my A, which I represent as ligand, they remain the same. So this is not what? An optical isomer. This is an optical isomer. So octahedral complexes, Talking about these octahedral complexes, I was able to represent the trans and the cis. This is the trans form, this is the trans form. Octahedral in the sense that 1, 2, 3, 4, 5, 6. Here, this is the cis. Over here is the 6. Over here is the 6. So that is just the brief explanation on the isomerism. So from my first slide, I was able to talk about what does isomers implies. So I talked about the type of isomer in coordination compounds, and first I defined the term isomer. I was able to talk about structural and stereoisomerism, and the subdivision of structural isomerism and stereoisomerism. So thank you very much for your attention.